Hello, in this lecture we will answer on two questions. In the first question we will find out the area of the semicircle, this semicircle that is inscribed by a quarter circle, and in the second question we will find out the size of this angle theta. This is actually the angle of the right triangle, triangle ABC. So we will start with the first question. In the drawing we have a quarter circle, and inside this quarter circle we have a semicircle that is inscribed by this quarter circle. We know that the radius of this quarter circle is equal to 3 units, and we want to find out the area of the semicircle that is inscribed by this quarter circle. So first of all, we will define the center of this quarter circle as point O. And then I will present to you a new rule that is actually rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. I'll repeat again on rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle, and we also have here tangent AB, we know that this tangent AB, is tangent to this circle at this point. Point M is the point of tendency. Of tangent AB with this circle. The center of this circle is at this point, point O, and we have the radius OM that we will define as R. Here the radius OM, it is drawn to the point of tendency, That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. Then whenever you have a radius that is drawn to the point of tendency, like in this drawing, the radius OM is drawn to the point of tendency, that is to say to point M, that is the point of tendency of tangent AB with this circle. Then according to rule number 1, the tangent will be perpendicular to that radius. In this case, tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO, that is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. Again, according to rule number 1, a tangent to a circle, that is to say tangent AB, is perpendicular to the radius, OM, that is drawn to the point of tendency. So whenever a radius is drawn to the point of tendency, like in this drawing, the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle, then the tangent will be perpendicular to that radius. AB will be perpendicular to radius MO. So this is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. Okay? So we actually can implement rule number 1 in our drawing. Here, first of all, we will define this point as point A, this point is point B, this point is point C. Here point C is the center of the contour circle. We define this point as point D, this point is point E, this point is point F, and this point is point G. We will join points O and B together by a straight line. Here, line segment OB is the radius of the semicircle. Why? Because line segment OB starts from the center of the semicircle, that is to say from point O, and ends at point B, that is a point of the semicircle itself. And this is exactly the definition of a radius. So OB is the radius of the semicircle, so we will define the radius of the semicircle as R, therefore OB will be equal to R. So here we have the radius OB, here the radius OB, the radius OB is drawn to the point of tendency, that is to say it is drawn to point B, that is the point of tendency of tangent AC with this semicircle, and whenever you have a radius that is drawn to the point of tendency like in this drawing, then the tangent will be perpendicular to that radius. Here, tangent AB will be perpendicular to the radius BO. So AB is perpendicular to BO, that is to say this angle equals to 90 degrees, and this angle will be equal to 90 degrees according to rule number 1. Likewise, we join points O and D together by a straight line. Here, line segment OD is the radius of the semicircle. Why? Because line segment OD starts from the center of the semicircle, that is to say from point O, and then at point D, that is a point on the semicircle itself. And this is exactly the definition of a radius. Therefore, OD is the radius of the semicircle, that is to say it is equal to R. And again, here we have the radius OD that is drawn to the point of tendency, that is to say it is drawn to point D, that is the point of tangent CE with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent CE will be perpendicular to the radius DO. So CE is perpendicular to DO, CE is perpendicular to DO, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Okay? Here, as I already said, C is the center of the quarter circle. I write it down. C is the center of the quarter circle, and angle ACE must be equal to 90 degrees. Here, because of the fact that ACE is a quarter circle, then angle ACE must be equal to 90 degrees. Angle ACE must be equal to 90 degrees, and C must be the center of the quarter circle. Okay, so in quadrilateral BOCD we have 3 right angles. I repeat again. In quadrilateral BOCD we have 1, 2, 3 right angles. 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3, that is 270 degrees, plus the size of the fourth angle, that is actually angle BOD, this angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtract 270 degrees from this equation, and we get that the missing angle BOD, is equal to 360 degrees minus 270 degrees, it is 90 degrees. So we found out that angle BOD is a right angle, it is equal to 90 degrees. So this angle is a right angle, BOD, equals to 90 degrees. So actually, quadrilateral BOCD has 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral BOCD, this quadrilateral, as a rectangle. So I write it down. Quadrilateral BOCD is a rectangle. And we have also rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. I write it down. The opposite sides of a rectangles are equal to each other. I will read rule number 2 again. According to rule number 2, the opposite sides of a rectangle are equal to each other. So, according to rule number 2, in rectangle BOCD, BO must be equal to CD, BO side BO must be equal to side CD, according to rule number 2, that the opposite sides of a rectangle are equal to each other. Okay, BO must be equal to CD according to rule number 2. But BO equals to R according to what we have already found out. BO equals to R. So BO equals to R. And from this equation R equals to BO equals to CD, we will derive that CD is also equals to R. CD is also equals to R. Here, CD equals to R. Likewise, according to rule number 2, OD must be equal to BC. Side OD must be equal to side BC, according to rule number 2, that the opposite sides of a rectangle are equal to each other. But we have already found out that OD equals to R. This is the radius of the semicircle. OD equals to R, so from this equation, R equals to OD equals to BC, we will derive that BC is also equals to R. Okay, BC is also equals to R, so here BC equals to R. So actually we found that all the sides of quadrilateral BOCD are equal to each other, they are equal to R, and all of its angles, they are right angles, they are equal to 90 degrees. Therefore, quadrilateral BOCD is not a rectangle but a square. So to write down that quadrilateral BOCD, according to what we have already found out, is a square. Okay. In the next step, we will join points C and D together, C, O and C together by a straight line. And we will find out the length of diagonal CO by implementing the Pythagoras theorem on the right grand triangle, triangle COD. CO is the diagonal of square BOCD. We find out the length of diagonal CO by implementing the Pythagoras theorem on the green right triangle, triangle COD. So according to the Pythagoras theorem, in the green right triangle, triangle COD, Here PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CO square equals to OD square plus CD square. I repeat again, in the right triangle COD, according to the Pythagoras theorem, CO square equals to OD square plus CD square. So CO square equals to OD square. Here, OD equals to R, so OD square is R square, plus CD square. CD is also equals to R, it is the radius of the semicircle, therefore CD square will be equal to R square. R square plus R square is 2R square. So in conclusion, we found out that CO square equals to 2R square. Here we take a root out of this equation and we get that CO, the diagonal of the square CO equals to square root of 2 times R. Square root of 2 times R. So here CO equals to square root of 2 times R. In the next step, we will extend the diagonal CO by a straight line until it touches the quarter circle at this point S. So what is the length of the new short line segment OS? The length of the short line segment OS, it is very easy to see from the drawing that the length of line segment OS equals to CS minus CO. Again, CS minus OC, or SC minus OC equals to OS. So OS, the length of the short line segment OS, will be equal to CS. Here, CS, what is the length of CS? C is the center of the quarter circle. S is a point on the quarter circle itself. And this is exactly the definition of a radius. That is to say, CS is the radius of the quarter circle that is equal to 3 units according to what is given us in the question. So CS is equals to 3 units. And we've already found out that OC or CO, it is the diagonal of the square of BOCD. That is to say, it is equal to square root of 2 times R. So, in conclusion, we actually found out that the length of the short line segment OS, it is equal to 3 minus square root of 2R. So we can write here that OS or SO equals to 3 minus square root of 2 times R. Okay. In the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and we will also extend diagonal OS by a straight line until it touches the circle at this point, point M. Point M is the touching point of the extended diagonal OC with this circle. What is the length of line segment CM? C is the center of the quarter circle, and M is the point on the circle itself. Actually, C is the center of the quarter circle and also the center of the circle itself. So any line segment that starts from the center of the circle and ends at any point on the circle itself, it is defined as a radius. So CM is the radius of the quarter circle, but it is also the radius of the circle itself. That is to say, CM equals to 3 units. Okay? So, in the next step, I will present to you a new rule. That is actually rule number 3. According to rule number 3, if chord AB intersects with chord CD at point O. Point O is the intersection point between chord AB and chord CD. Then the following formula is true, that AO times OB is equal to CO times OD. I repeat again, on rule number 3, according to rule number 3, if chord AB intersects with chord CD at point O, again point O is the intersection point, then the following formula is true, that AO times OB equals to CO times OD. So what is the meaning of rule number 3? The meaning of rule number 3 is that if we have chord AB, this is chord AB inside the circle, that intersects with chord CD. This is chord CD. And the intersection point between chord AB and chord CD is at this point, point O. Then, according to rule number 3, we will get that AO times OB equals to CO times OD. Okay, again, AO times OB equals to CO times OD. So we can implement rule number 3 in our drawing. Why? Because in our drawing, we have chord SM that intersects with chord GE at point O. Okay, so I'll write it down. In our drawing, we have chord SM. This chord intersects with chord GF, this chord, at point O. Point O is the intersection point between chord SM and chord GF. I will repeat again. In our drawing, we have chord SM intersects with chord GF at point O. Point O is the intersection point. Therefore, according to rule number 3, we will get that MO times OS, again, MO times OS equals to GO times OF. GO times OF. I'll repeat again. According to rule number 3, we get that MO times OS equals to GO times OF. Again, MO times OS equals to GO times OF. What is the length of line segment MO? We can see from the drawing, it is very easy to see from the drawing that the length of line segment MO equals to MC plus CO. Again, MO equals to MC plus CO, and we have already found out that the length of the short line segment OS equals to 3 minus square root of 2R. I repeat again, OS equals to 3 minus square root of 2r, MO equals to MC plus CO, and it is equal to GO. What is the length of line segment GO? O is the center of the semicircle. G is the point of the semicircle itself, and this is exactly the definition of a radius. Any line segment that starts from the center of the semicircle and ends at any point on the semicircle itself, it is defined as a radius of the semicircle. Therefore, GO is the radius of the semicircle, that is to say, it is equal to R. For the same reason, OE, line segment OE will be also equal to R. Why? Because it starts from the center of the semicircle, that is to say from point O, and ends at point E, that is a point on the semicircle itself. Therefore, OE is the radius of the semicircle, that is to say, it is equal to R. So GO equals to R, and OF is also equals to R. R times R is R squared. So in this side of the equation we have R squared, and here we have 3 times square root of 2R times MC. MC equals to 3 units, so we substitute MC by 3 plus CO. We have already found out that CO, the diagonal CO, equals to square root of 2 times R. So in conclusion, we found out that 3 plus square root of 2R times 3 minus square root of 2R equals to R squared. This expression, 3 plus square root of 2r times 3 minus square root of 2r, it is very similar to the algebraic identity that a plus b times a minus b equals to a squared minus b squared. In our specific expression, A is equal to 3 and B equals to square root of 2R. And A plus B times A minus B equals to A squared minus B squared. That is to say, this expression equals to A squared minus B squared. A is 3. So A squared is 3 squared, that is 9. Minus B squared. B is square root of 2R. Square root of 2R squared equals to square root of 2 squared, that is 2, times R squared. So square root of 2R squared equals to 2R squared. So A squared minus B squared will be equal to 9 minus 2R squared. And this expression equals to R squared. So this expression will be also equal to R squared. So in conclusion, we found out that 9 minus 2R squared equals to R squared. Here we will add 2R squared to this equation, and we get that 9 equals to R squared plus 2R squared is 3R squared. We divide this equation by 3, and we get that R squared, 3R squared over 3 is R squared. R squared equals to 9 over 3, this is 3. So we found out that R squared equals to 3. And what is the area of the semicircle? The formula for the area of any circle is pi r squared. So the area of the semicircle will be equal to half of it. That is to say, it will be equal to pi r squared over 2. So the area of the semicircle equals to pi r squared over 2. So it is pi, r squared is 3, so we will substitute r squared by 3 over 2. So it is actually equals to 3 pi over 2 square units. So in terms of numbers, it is equals to 4.71 square units. Okay. I'll repeat again. The area of this semicircle equals to either 3 pi over 2 square units, so in terms of numbers, it is equal to 4.71 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this semicircle according to the second method. In the second method, we will use all the things that we have already found out in the first method. So here, this point is point A, this point is point B, this point is point C, it is the center of the quarter circle. This point is point D, this point is point E. This point is point F, this point is point G, and this point is point S. This point is actually point O. We have already found out that BOCD is a square. And the diagonal of C of square BOCD is equal to square root of 2 times R. We will join points C and G together by a straight line. Here, line segment CG is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle, that is to say from point C, and ends at point G, that is a point on the quarter circle itself. Therefore, CG is the radius of the quarter circle, that is to say it is equal to 3 units. Likewise, from the same reason, if we join points C and F together by a straight line, CF will be also equal to the radius of the quarter circle, that is to say it will be equal to 3 units. Okay. So here we have the right triangle. Actually, we have triangle CGF. So we will copy the right triangle CGF in a new page, and we'll analyze the right triangle. We'll analyze the triangle CGF. Okay. Here we've already found out in the first method that GO is the radius of the semicircle, that is to say it is equal to R, and FO, it is also the radius of the semicircle, that is to say it is also equal to R. So this is the triangle CFG, that I copied from the original drawing. In triangle CFG, we know that side CF equals to side CG equals to 3 units. CF equals to CG equals to 3 units. Therefore, triangle CFG is an isosceles triangle. Because it has two sides that are equal to each other, it is an isosceles triangle. In the isosceles triangle, triangle CFG, we know that FG is the base of the isosceles triangle. Okay, so FG, right here that FG is the base of the triangle. And what is 9 segment CO? 9 segment CO bisects the base PC into two equal parts. That is to say FO equals to OG equals to R. And because of the fact that 9 segment CO divides the base BO, 9 segment CO divides the base FG into two equal parts, this is exactly the definition of a median. So CO is the median to the base FG. CO is the median to the base FG because it divides the base FG into two equal parts. And we also have rule number 4 that is related to the median to the base of an isosceles triangle. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So I read rule number 4 again. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So here, according to rule number 4, if we focus on this drawing, we have the median CO to the base FG, and according to rule number 4, the median CO to the base FG is perpendicular to the base FG. That is to say CO is perpendicular to FG. CO is perpendicular to FG. That is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 4. Okay, again, the median CO to the base FG is perpendicular to the base FG. That is to say, CO is perpendicular to FG. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. So here, in the original drawing, according to rule number 4, the median CO to the base CF is perpendicular to the base GF. So CO is perpendicular to GF. If CO is perpendicular to GF, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. So we'll focus on the right triangle COG, and we'll implement the Pythagoras theorem on the right triangle COG. Okay, we will implement the Pythagoras theorem on the right triangle COG. We know that side OG equals to R, CG equals to 3 units, and the median CO equals to square root of 2 times R. So we'll implement the Pythagoras theorem in this right triangle COG. According to the Pythagoras theorem, in the right triangle COG, in the given this given right triangle COG, according to the Pythagoras theorem, PT is a relation for Pythagoras theorem. We get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CG square equals to CO square plus OG square. CG is 3, so CG square is 9, and it equals to CO square. CO is equal to 2 times R, so CO square will be equal to 2R square. Why? Because it is square root of 2 squared, that is 2 times R square. So in conclusion, it is 2R square plus OG square. OG equals to R, so OG square is R square. So in conclusion, we found out that 2R square plus R square, it is 3R square. So 9 equals to 3R square. We'll divide this equation by 3, and we'll get that R square equals to 3. And the area of the semicircle is equals to pi R square over 2. So it is pi, R square is 3, so we'll substitute R square by 3 over 2. So in conclusion, we found out that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. Okay, so we finished with the second method. In the next step, I will present to you the question number 2. We solve the second question in two different methods. In the drawing, we have the right triangle, triangle ABC. Angle ABC equals to 90 degrees. Side BC of the right triangle ABC equals to 6 units. Line segment DE equals to 2 units. We also know that line segment AE equals to EC. And we want to find out the value of this angle, angle BAC, that is actually equals to theta. So we found out the size of this angle, angle theta. We start with the first method. In the first method, we will do a construction. From point E, we will draw perpendicular on BC. Again, from point E, we will draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point E and BC as F. In the next step, we will define angle ACB as alpha. So angle ACB equals to alpha according to our definition from one side. But from the other side, this angle, angle ACB, it is also equals to, in the right triangle ABC, this angle equals to 90 degrees, this angle equals to theta. So the first angle, this angle, angle ACB, must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC to 180 degrees. This angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. So, from one side this angle equals to alpha, from the other side it is equal to 90 degrees minus theta. So we can derive from it that alpha equals to 90 degrees minus theta. Okay, angle alpha equals to 90 degrees minus theta. Here we will add theta to this equation and we will subtract alpha, and we will get that theta equals to 90 degrees minus alpha. Okay? In the small right triangle, triangle FEC, we have one angle, this angle equals to 90 degrees, this angle equals to alpha, so this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right triangle, 280 degrees, this angle must be equal to 90 degrees minus alpha. But because of the fact that we have already found out that 90 degrees minus alpha equals to theta, so this angle equals to theta also. And what is the size of this angle, angle DEF? Angle DEF equals to angle DEC, the big angle, angle DEC, minus angle FEC. It is very simple to see from the drawing that the big angle, angle DEC, minus angle FEC will give us this angle that is actually angle DEF. So I write it down. Angle DEF, this angle equals to angle DEC, the big angle, angle DEC, minus this angle that is actually angle FEC. I repeat again, angle DEF equals to the big angle DEC minus angle FEC. So angle DEF is equals to angle DEC. According to what is given in the question, this angle equals to 90 degrees. So we substitute angle DEC by 90 degrees minus, we have already found out that this angle FEC equals to 90 degrees minus alpha. So we substitute angle FEC by 90 degrees minus alpha. So here we will open the brackets and we will get that the missing angle DEF equals to 90 degrees minus 90 degrees, it is 0, and here we have minus with minus, it is plus, so it is plus alpha. So in conclusion, we found out that the missing angle DEF equals to alpha. Okay, so angle DEF equals to alpha. This angle DEF equals to alpha. So in the right triangle DEF, this angle equals to 90 degrees, this angle equals to alpha. So this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right triangle DEF. 280 degrees, this angle must be equal to 90 degrees minus alpha. But because of the fact that we have already found out that 90 degrees minus alpha equals to theta, we can substitute 90 degrees minus alpha by theta. We will do it now, and we get here that this angle that is equal to 90 degrees minus alpha, it is equal to theta according to the question that I presented to you. This angle equals to theta. In the next step, we will define side DF as x, side EF as y. We will define line segment AE as A. So we know that AE equals to EC according to what is given us the question. So if AE equals to EC and AE equals to A, then EC must be also equal to A. In the next step, we will prove that the right big triangle ABC is similar to the small right triangle EFC. Okay, I will write it down. We will prove that the right big triangle ABC is similar to the small right triangle EFC. So why triangle ABC is similar to the right triangle EFC? First of all, those two angles are equal to each other because they are both equal to 90 degrees, therefore they are equal to each other. So angle ABC of triangle ABC is equal to this angle that is actually angle EFC, and both those angles are equal to 90 degrees. I will repeat again. angle ABC equals to angle EFC, and they are both equal to 90 degrees. In addition, those two angles, they are both equal to theta, therefore they are equal to each other. So angle BAC of triangle ABC is equal to this angle that is actual angle FEC, and both angles are equal to theta. I'll repeat again, angle BAC of triangle ABC equals to angle FEC of triangle FEC, and they are both equal to theta. Finally, this angle is a common angle, it belongs to both triangles. It is very easy to see that this angle belongs to the right B triangle, triangle ABC, and it is also belongs to the small right triangle, triangle EFC. So we can write down that angle BCA equals to angle ECF, that is equal to alpha, and they are equal to each other, or it is a common angle. So we actually say here that this angle equals to itself. Okay. So angle BCA equals to angle ECF. It's a common angle that belongs to both triangles. So we actually proved that all three angles of triangle ABC can go into all three angles of triangle EFC. Why? Because those two angles are equal to each other, they are both equal to theta, therefore they are equal to each other. Those two angles are both equal to 90 degrees, therefore they are equal to each other. And this angle is a common angle that belongs to both triangles, therefore it is equal to itself. So we actually proved that all the angles of triangle ABC can go into all the angles of triangle EFC, therefore triangle ABC, the big right triangle, is similar. This is the sign of similar to the right triangle, triangle EFC. According to angle similarity rule. Okay, and from the fact that triangle ABC is similar to triangle EFC, we will conclude, hence, AB over AC, in the triangle ABC, AB over AC is equal to EF over EC in the triangle EFC. I repeat again, from the fact that triangle ABC is similar to triangle EFC, we conclude that AB over AC equals to EF over EC. So here AB over AC, the hypotenuse AC equals to A plus A, that is to say it is equals to 2A according to our definition. So we substitute the hypotenuse AC by 2A. And it is equal to EF. EF equals to Y. So we substitute EF by Y over EC. EC equals to A, so we substitute EC by A. So in conclusion, we found out that according to equation number 1, AB over 2A equals to Y over A. Here we have A on both sides of equation number 1, so A will get cancelled. and we're left only with AB over 2, that is equal to y, according to equation number 1. Here we will multiply by 2 this equation number 1, and we get that according to equation number 1, AB equals to 2y. So we can write here that AB equals to 2y. In the next step, we'll prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle EDF. So, triangle ABC, the big right triangle, triangle ABC, we prove that it is similar to the small right triangle, this right small triangle EFD, this triangle EFD. So why the right triangle ABC is similar to the right triangle EFD? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So angle ABC of triangle ABC is equal to this angle that is actually angle EFD, and they are both equal to 90 degrees. I'll repeat again, angle ABC equals to angle EFD, and they are both equal to 90 degrees. In addition, those two angles, they are both equal to alpha, therefore they are equal to each other. So angle ACB of triangle ABC equals to angle DEF, and they are both equal to alpha. And repeat again, angle ACB equals to angle DEF, and they are both equal to alpha. And finally, those two angles, they are both equal to theta, therefore they are equal to each other. Okay, so angle BAC equals to angle FDE, this angle, and they are both equal to theta. I repeat again, angle BAC equals to angle FDE, and they are both equal to theta. So we prove that all the angles of triangle ABC can go into all the angles of this right triangle, triangle EDF. Why? Because those two angles, they are both equal to alpha, therefore they are equal to each other. Those two angles, they are both equal to theta, they are both equal to theta, therefore they are equal to each other. And those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So triangle ABC is similar to the right triangle EDF. Triangle ABC is similar to the right triangle, triangle EDF, according to angle similarity rule. Okay, and from the fact that triangle ABC is similar to triangle EDF, we will derive that AB over BC in the right triangle ABC is equal to DF over EF in the right triangle EDF. I will repeat again. From the fact that triangle ABC is similar to triangle EDF, we will derive that AB over BC in the right triangle ABC equals to DF over EF in the right triangle EDF. So here AB equals to 2y and BC equals to 6 units according to what is given us in the question. And it is equal to df that is x according to our definition over df that is over ef that is actually y. So in conclusion, we found out that according to equation number 2, 2y over 6 equals to x over y. Here we divide both the numerator and the denominator of this side of equation number 2 by 2, and we will get that 2y over 2 is y and 6 over 2 is 3. So in conclusion, y over 3 equals to x over y. We'll cross multiply this equation number 2, and we get that y squared equals to 3x. So according to equation number 2, we found out that y squared equals to 3x. In the next step, we will focus on the right small triangle EDF. In the right small triangle EDF, according to the Pythagoras theorem, it is very easy to see from the knowing that x squared plus y squared equals to 2 squared. In the right triangle EDF, according to the Pythagoras theorem, if PT is abbreviation for Pythagoras theorem, x squared plus y squared equals to 2 squared, that is 4. So here we can substitute y squared in equation number 3 by 3x because x equals to y squared according to equation number 2. We will do it now and we will get that according to equation number 3, x squared plus y squared, but y squared according to equation number 2 is 3x equals to 4. Here we subtract 4 from this equation number 3. And we will get that according to equation number 3, x squared plus 3x minus 4 equals to 0. So we have here equation number 3 is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b and c are the coefficients of the quadratic equation, and x is the variable that we are looking for, and we will find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a in our specific quadratic equation. The coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we put the data inside the equation and we find out the value of the values of x. According to this formula, x equals to minus b, b is 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9. Minus 4 times a is 1, and c is minus 4 over 2a. A is 1, so 2 times 1 is 2. So, actually found out that x equals to minus 3 plus minus, and here we have minus 4 times minus 4 is plus 16, and 16 plus 9 is 25. So inside the root we have left only with 25 over 2. So we actually found out that x equals to minus 3 plus minus the square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So I found out that x1, the first solution for x is x1 equals to minus 4. But because of the fact that ax is the length, as x is the length of side df of the right triangle EDF, it must be a positive number. So write it down. X is a length, and as a length it must be a positive number. It can never be equal to minus 4, that is a negative number. So we cancel this solution, and we will left only with the solution, the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So I found out that x2 equals to 1. So I will copy the right triangle EDF, and we will find out the cosine theta of the right triangle EDF. So this is the right triangle EDF that I copied from the original drawing. In this right triangle EDF, we know that cosine theta equals to df over dE. df equals to x, that is equal to 1, and d equals to 2 according to what is given us in the question. So in conclusion, we found out that cosine theta equals to 1/2. So if cosine theta equals to 1/2, it means that theta itself equals to 60 degrees. So we found out that theta equals to 60 degrees. The answer to the question that this angle, the angle that we are looking for, angle theta, equals to 60 degrees. We finish with the first method. In the next step, I will present to you how to find out the size of angle theta according to the second method. In the second method, we define this angle as angle alpha as we did in the first method, and we have already found out that alpha equals to 90 degrees minus theta. So we will focus on the right triangle ABC. So I will copy the right triangle ABC in the new page, and we will analyze the right triangle ABC. But first of all, we will define AE as A, so EC will be also equal to A. That's the thing that we already did in the first method. So AE equals to A, and EC will be also equal to A. Therefore, the hypotenuse AC of the right triangle ABC will be equal to A plus A, that is 2A. So this is the right triangle ABC that I copied from the original drawing. In the right triangle ABC, cosine alpha equals to BC over AC. BC equals to 6 units according to what is given in the question, and AC equals to 2A according to our definition. So here we will divide both the numerator and the denominator of this side of equation number 1 by 2, and we get that 6 over 2 is 3, and 2A over 2 is A. So in conclusion, we found out that according to equation number 1, cosine alpha equals to 3 over A. Here we will multiply equation number 1 by A, and then we will divide it by cosine alpha, and we will get that according to equation number 1, A equals to 3 over cosine alpha. Okay, we found out that according to equation number 1, A equals to 3 over cosine alpha. In the next step, we will focus on the right triangle DEC. So I will copy the right triangle DEC in the new page, and we will analyze the right triangle DEC. So I copied the right triangle DEC from the original drawing. In the right triangle DEC, we know that tangent alpha equals to DE over EC. DE equals to 2, EC equals to A. So in conclusion, found out that according to equation number 2, tangent alpha equals to 2 over a. But according to equation number 1, we have already found out that a equals to 3 over cosine alpha. So we can substitute a in equation number 2 by 3 over cosine alpha, because 3 over cosine alpha equals to a according to equation number 1. We will do it now, and we will get that according to equation number 2, times alpha equals to 2 over a, and a according to equation number 1, it is equal to 3 over cosine alpha. So we get here that according to equation number 2, times alpha equals to 2 times cosine alpha over 3. We know that tangens alpha equals to sinus alpha over cosine alpha, so we'll substitute tangens alpha by sinus alpha over cosine alpha. And we will get that according to equation number 2, sinus alpha over cosine alpha equals to 2 times cosine alpha over 3. Here we'll cross multiply this equation number 2, and we'll get that according to equation number 2, 3 times sine alpha equals to 2 times cosine square alpha. We have the trigonometric identity that sinus square alpha plus cosine square alpha equals to 1. We'll substitute sinus square alpha from this equation, from this trigonometric identity, and we'll get that cosine square alpha equals to 1 minus sinus square alpha. Now we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha according to this trigonometric identity. So we do it now, and we get that 3 sinus alpha equals to 2 times cosine square alpha, and cosine square alpha according to this trigonometric identity equals to 1 minus sinus square alpha. Here we will open the brackets of this equation number 2, and we get that 3 sine alpha equals to 2 times 1 is 2, and 2 times minus sinus square alpha equals to minus 2 times sinus square alpha. We will add 2 times sine square alpha to this equation number 2. And we get that according to equation number 2, two times sine square alpha plus 3 times sine alpha equals to 2. Here we will subtract 2 from this equation number 2, and we get that according to equation number 2, two times sine square alpha plus 3 sine alpha minus 2 equals to 0. So here we have a quadratic equation. The coefficient A in this quadratic equation equals to 2. The coefficient B equals to 3. And the coefficient C equals to minus 2. And the variable that we are looking for is sinus alpha, so x equals to sinus alpha. And the general formula for solving the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So we'll put the data inside the formula for x and we find out the value of the values of sinus alpha, because x equals to sinus alpha. So we get that sinus alpha equals to minus b. B is 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9, minus 4 times a is 2, and c is minus 2, over 2a. A is 2, so 2a is 2 times 2, that is 4. So we actually found out that sinus alpha equals to minus 3 plus minus square root of minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16, and 16 plus 9 is 25. So inside the root we left only with 25 over 4. So sinus alpha equals to minus 3 plus minus the square root of 25 is 5 over 4. So here we will have two solutions that are possible for sinus alpha. The first solution is that sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So, in conclusion, we found out that according to the first solution, for sinus alpha equals to minus 2. But because of the fact that the function sinus can accept values that are ranging from minus 1 to plus 1, and minus 2 exceeds this range of values that sinus alpha can accept, this solution is a correct solution. So we cancel the solution, or in other words, sinus alpha can never be equal to minus 2. So we cancel the solution, and we left only with the second solution for sinus alpha. The sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 half. So we found out that sinus alpha equals to 1 half. And if sinus alpha equals to 1 half, alpha itself must be equal to 30 degrees. So we found out that alpha equals to 30 degrees. And we have this equation that alpha equals to 90 degrees minus theta. Alpha equals to 90 degrees minus theta. Alpha equals to 30 degrees, so we substitute alpha in this equation by 30 degrees. We will do it now, and we will get that 30 degrees equals to 90 degrees minus theta. Here we will add theta to this equation, and we subtract 30 degrees, and we will get that theta equals to 90 degrees minus 30 degrees. That is 60 degrees. So we found out that the angle that we are looking for, angle theta, equals to 60 degrees according to the second method also. So the angle that we are looking for, this angle theta, equals to 60 degrees in its size. Okay? according to the second method. So we finish with the second method. In the next step, I will summarize the lecture. We start with the first question. In the first question, we have a semicircle that is described by this quarter circle. We know that the radius of the quarter circle is equal to 3 units, and we want to find out the area of the semicircle that is described by the quarter circle. So we define the center of the semicircle as point O here, and then I present it to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have tangent AB of this circle that is tangent to this circle at point M is the point of tendency of tangent AB with this circle, then according to rule number 1, and we have also the center of this circle is at point O. So here the radius OM of this circle, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. Here, AB will be perpendicular to MO. So this angle equals 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So we can actually implement rule number 1 in our drawing, because here we have the radius OB that is drawn to the point of tendency, that is to say the radius OB is drawn to point B, that is the point of tendency of tangent AC with this circle, and whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, in this case, tangent AC will be perpendicular to BO. So AC is perpendicular to BO, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we connected points O and D together by a straight line. Here, the radius OD, it is drawn to the point of tendency, that is to say, it is drawn to point D, that is the point of tendency of tangent CE with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, tangent CE will be perpendicular to the radius DO. So CE perpendicular to DO, that is to say, this angle equals 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. And we also know that C is the center of the quarter circle. Because of the fact that ACE is a quarter circle, C must be the center of the quarter circle, and angle ACE must be equal to 90 degrees. Therefore, quadrilateral BOCD, we have 3 right angles, 1, 2, 3, and the sum of 3 right angles is 90 times 3, that is 270 degrees, plus the size of the fourth angle, that is actually angle BOD. In total, they must be equal, those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation and found out that the missing angle BOD equals to 360 degrees minus 270 degrees, it is 90 degrees. So this angle, the missing angle equals to 90 degrees. So in quadrilateral BOCD, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral BOCD as a rectangle. Here, quadrilateral BOCD is a rectangle. Then I present it to you rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. So according to rule number 2, the opposite sides of a rectangle BOCD, they are equal to each other. That is to say, BO equals to CD. According to rule number 2, BO equals to CD. But we have already found out that BO equals to R. So according to this equation, R equals to BO equals to CD, we will derive that CD is also equals to R. Here CD equals also to R. Likewise, according to rule number 2, OD must be equal to BC. OD must be equal to BC according to rule number 2. But OD equals to R. According to what we have already found out, OD equals to R. So from this equation, R equals to OD equals to BC, we will derive that BC is also equals to R. So in quadrilateral BOCD, we have 4 equal sides, all of its sides are equal to R, and it has also 4 right angles. Therefore, quadrilateral BOCD is not a rectangle but a square. Then we join points O and C together by a straight line. OC is the diagonal of square BOCD. We found out the length of diagonal OC by implementing the Pythagoras theorem on the right triangle COD, the right triangle, triangle COD. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here CO square equals to OD square plus CD square. CO square equals to OD square plus CD square. So CO square equals to OD square, OD equals to R, so OD square is R square, plus, so OD square is R square plus CD square. CD is R, so CD square is R square. So here, OD square plus CD square is R square plus R square, that is 2R square. So in conclusion, we found out that CO square equals to 2R square. We took a root out of this equation, and we found out that the diagonal CD of square BOCD equals to square root of 2 times R. So CO equals to square root of 2 times R. Then we extended the diagonal CO until it touches the quarter circle at point S. And we found out the length of the small line segment SO or OS. OS equals to SC, or SC minus OC equals to OS. OS equals to SC minus OC. So SC is the radius of the quarter circle because line segment SC starts from the center of the quarter circle and ends at point S, that is the point of the quarter circle itself. Therefore, SC equals to the radius of the quarter circle, that is to say it is equal to 3 units, minus OC. OC equals to square root of 2 times R, according to what we have already found out. So in conclusion, we found out that line segment OS equals to 3 minus square root of 2R. Okay? The short line segment OS equals to 3 minus square root of 2 times R. Then we completed the quarter circle to a circle, and we extended the diagonal OC until it touches the circle at point M. What is the length of CM? C is the center of the circle and also the center of the quarter circle. M is the point of the circle itself, and this is exactly the definition of a radius. That is to say, CM is the radius of the circle, that is also the radius of the quarter circle, that is to say, CM equals to 3 units. Then I presented to you rule number 3. According to rule number 3, if chord AB intersects with chord CD at point O, then the following formula is true, that AO times OB equals to CO times OD. Here, chord AB intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. So if this is the things that we have here, if this is the reality, then according to rule number 3, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Okay, so we can implement rule number 3 in our drawing. Why? Because in our drawing we have chord SM that intersects with chord GF at point O. I'll repeat again. Chord SM intersects with chord GF at point O. Therefore, according to rule number 3, we get that MO times OS equals to GO times OF. Okay? Repeat again, according to rule number 3, MO times OS equals to GO times OF. What is the length of MO? MO equals to MC plus CO. MO equals to MC plus CO. And we already found out that OS equals to 3 minus square root of 2R. MC equals to 3 units. This is the radius of the circle. CO equals to square root of 2 times R. So in conclusion, MC plus CO equals to 3 plus square root of 2R times 3 minus square root of 2R equals to, here, GO is the radius of the semicircle because it starts from the center of the semicircle and ends at point G, that is the point of the semicircle itself. For that reason, for the same reason, OF is also the radius of the semicircle, that is to say it is equal to R. So in conclusion, we found out that GO times OF equals to R times R, that is R squared. In conclusion, we found out that 3 plus square root of 2 times R times 3 minus square root of 2R equals to R squared. This expression is very similar to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. So this expression, according to this trigonometric identity, must be equal to A squared minus B squared. In our specific expression, A equals to 3 and B equals to square root of 2 times R. So A squared will be equal to 3 squared, that is 9, minus B squared. B squared will be equal to 2R squared. So in conclusion, A squared minus B squared will be equal to 9 minus 2R squared, and it is equal to R squared. Here we added 2R squared to this equation and we found out that 2R squared plus R squared is 3R squared, so here 9 equals to 3R squared. We divided this equation by 3 and we found out that R squared equals to 3. The area of the semicircle equals to pi R squared. R squared equals to 3, so we can substitute R squared by 3. So in conclusion, we found out that the area of the semicircle according to the first method equals to either 3 times pi over 2, or in terms of numbers, it is equal to 3.71 square units. We finished with the first method. Then we found out the area of the semicircle according to the second method. In the second method, we used the things that we already found out in the first method. We already found out that BOCD is a square, and the diagonal CO of the square, BOCD equals to square root of 2 times R. We joined point C, and we already found out that GO equals to OF equals to R. It is the radius of the semicircle. We joined point C and G together by a straight line. CG is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle, that is to say from point C, and ends at point D, that is the point of the quarter circle itself. Therefore, CG is the radius of the quarter circle, that is to say it is equal to 3 units. For the same reason, CF will be also the radius of the quarter circle, that is to say it is equal to 3 units. So I copied the associated triangle CGF in a new page, and we analyzed the triangle CGF. So because of the fact that CF equals to FG, we can conclude from it that triangle CFG is an isosceles triangle, and the base of this isosceles triangle, triangle CFG, is FG. And here CO that is equal to square root of 2 times R. It is the median to the base. Why? Because the median to the base bisects the base into two equal parts. Here FO equals to OG equals to R. Because of the fact that line segment CO bisects the base FG, CO must be equal to the median to the base, because it bisects the base into two equal parts. And we have rule number 4 that states that the median to the base in an isosceles triangle is perpendicular to the base. So, according to rule number 4, the median CO to the base FG is perpendicular to the base FG. So CO is perpendicular to FG. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. Here also, the median CO is perpendicular to the base GF. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. So I copied the right triangle CGO in a new page, this right triangle, and we implemented the Pythagoras theorem in the right triangle CGO. Here, in the right triangle CGO, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CG square equals to CO square plus GO square. CG equals to 3, so CG square is 3 squared, that is 9, plus CO square. CO equals to square root of 2 times R, so CO square is 2R square, plus GO square. GO equals to R, so GO square is R square. So in conclusion, found out that 9 equals to 2R square plus R square. 2R square plus R square is 3R square, so 9 equals to 3R square. We divided this equation by 3 and found out that R square equals to 3, and the R of the semicircle equals to pi R square over 2. We substituted R square by 3, because R square equals to 3, and found out that the R of the semicircle according to the second method equals to either 3 pi over 2 square units, or in terms of numbers it is equal to 3.71 square units. So we finished with the first question. Then I presented to you the second question. We solved the second question in two different methods. In the first method, we have here the right triangle ABC. Side BC equals to 6 units. Angle ABC equals to 90 degrees. Line segment OE equals to 2 units. And we know that this angle equals to 90 degrees, this angle equals to 90 degrees. AE equals to EC. And we want to find out the size of this angle theta. So here, in the first method, we made a construction. From point E, we drew a perpendicular on BC. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We defined the touching point of the perpendicular from point E and BC as F. Then we define this angle ACB as alpha. So here, in the right triangle ABC, if this angle equals to theta and this angle equals to 90 degrees, this angle must be equal to 90 degrees minus theta. So from one side, this angle equals to alpha. From the other side, it must be also equal to 90 degrees minus theta. So from those two things, we will conclude that alpha equals to 90 degrees minus theta. So alpha equals to 90 degrees minus theta. Here we added theta to this equation and we subtracted alpha, and we found out that theta equals to 90 degrees minus alpha. Okay, then here we have this angle in the right triangle EFD, we have this angle that is equal to alpha. This angle equals to 90 degrees, so this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in the right triangle EFC to 180 degrees. This angle must be equal to 90 degrees minus alpha. So, but 90 degrees minus alpha According to this equation, 90 degrees minus alpha equals to theta. So we can write here that 90 degrees minus alpha equals to theta. And we found out the size of this angle DEF. Angle DEF equals to angle DEC minus angle FEC. I'll repeat again, angle DEF equals to the right bigger angle DEC minus angle FEC. Angle DEC equals to 90 degrees according to what is given as the question. And we have already found out that angle FEC equals to 90 degrees minus alpha. We opened the brackets here and we found out that 90 degrees minus 90 degrees is 0 and minus is plus. So in conclusion we found out that the missing angle here, angle DEF equals to alpha. So in the right triangle DEF, if this angle equals to alpha, this angle equals to 90 degrees, this angle must be equal to 90 degrees minus alpha. But because of the fact that 90 degrees minus alpha equals to theta, we can substitute 90 degrees minus alpha by theta. We did it and we defined this angle as angle theta. Then we proved that the right triangle ABC is similar to the right triangle EFC according to angle similarity rule. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to 90 degrees. So for they are equal to each other. Those two angles, they are both equal to theta, therefore they are equal to each other, and this angle is a common angle that belongs to both triangles. So we actually proved that all the angles of triangle ABC can go into all the angles of triangle EFC. Therefore we proved the triangle ABC is similar to triangle EFC according to angle similarity rule. And from the fact that triangle ABC is similar to triangle EFC, we will conclude that AB over AC equals to FE over EC. Okay, AB over AC triangle ABC equals to EF over EC triangle EFC. Okay, so AB over AC. AC equals to A plus A, so we can sum A plus A is 2A, so we can substitute AC by 2A, and it is equal to EF. EF equals to Y according to our definition, and EC equals to A according to our definition. So in conclusion, we found out that AB over 2A equals to Y over A. Here we have A on both sides of the equation. So A will get cancelled. And we left only with AB over 2 that is equal to Y. We multiply the equation number 2 by, we multiply the equation number 1, this equation by 2, and we found out that AB equals to 2Y. So here we can write down that AB equals to 2Y. Then we proved that the right big triangle ABC is similar to the right small triangle, this triangle EDF. Okay, so why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. Those two angles, they are both equal to theta, therefore they are equal to each other. Those two angles, they are both equal to alpha, therefore they are equal to each other. So we proved that all the angles of triangle ABC can go into all the angles of triangle DEF. Therefore triangle ABC is similar. Triangle ABC is similar to triangle EDF according to angle similarity rule. And from the fact that triangle ABC is similar to triangle EDF, we will derive that AB over BC equals to DF over EF. Again, AB over BC triangle ABC equals to DF over EF. AB equals to 2Y, BC equals to 6, D equals to X, and EF equals to Y. So in conclusion, we found out that 2Y over 6 equals to X over Y. Here we divided both the numerator and the denominator of this side of equation number 2 by 2, and we got that 2Y over 2 is Y, and 6 over 2 is 3. So in conclusion, we found out that Y over 3 equals to X over Y, because multiply this equation number 2, and found out that Y squared equals to 3X. In the right triangle EDF, in this right triangle, it is very easy to see that according to the Pythagoras theorem, x squared plus y squared equals to 2 squared. So according to equation number 3, in the right triangle ABC, according to the Pythagoras theorem, x squared plus y squared equals to 2 squared, that is 4. So we can substitute y squared in this equation number 3, by 3x, because y squared equals to 3x, according to equation number 2. We did it. And we found out that x squared plus y squared, that is 3x, equals to 4. We subtracted 4 from this equation number 3, and we found out that x squared plus 3x minus 4 equals to 0. So we have here a quadratic equation. The general form of a quadratic equation is ax squared plus bx plus 3 equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we found out the value of x according to the following formula, that x equals to minus b plus minus 4 of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we put the data inside the formula for x, and we find out the values of x. Here, x equals to minus b, b is 3, so minus b is minus 3, plus minus b squared, b is 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, and c is minus 4, so it is minus 4 times minus 4 over 2a. A is 1, so 2 times 1 is 2. So inside the root we have minus 4 times minus 4 is 16, and 16 plus 9 is 25. So in conclusion, we found out that x equals to minus 3 plus minus, and inside the root we left only with 25 over 2. The square root of 25 is 2. So in conclusion, we found out that x equals to minus 3 plus minus the square root of 25 is 5. So it is x equals to minus 3 plus minus 5 over 2. So here we have two solutions that are possible for x. The first solution for x is x equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. But because of the fact that ax is the length of side df of the right triangle DEF, it must be a positive number. So x can never be equal to minus 4, that is a negative number. So we cancel that solution, and we left only with the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So I copied the right triangle DF in a new page, and we implemented, actually here we found out the value of cosine theta in this right triangle. Here, this is the right triangle in DF. We just right now found out that x equals to 1, ED equals to 2 according to what is given as the question, and this angle is angle theta. So according to, in the right triangle in DF, cosine theta equals to DE over ED. Okay? So DE equals to 1. ED equals to 2, so in conclusion found out that cosine theta equals to 1 half. If cosine theta equals to 1 half, it means that theta itself equals to 60 degrees. So we found out that the size of this angle theta, is 60 degrees. We finished with the first method, then I presented to you how to find out the size of angle theta according to the second method. In the second method, we define this angle as angle alpha. We have already found out that alpha equals to 90 degrees minus theta according to the first method. We defined AE as A, and EC must be also equal to A because A equals to EC. Then we focused on the right triangle ABC. So I copied the right triangle ABC in the new page, and we implemented here. We analyze the right triangle ABC. We know that side BC equals to 6 units. It is given as the equation. This again equals to alpha according to our definition. And the hypotenuse AC equals to A plus A, that is 2A according to our definition. So here, in this right triangle, we know that cosine alpha equals to BC over AC. BC equals to 6 and AC equals to 2A. So in conclusion, we found out that according to equation number 1, cosine alpha equals to 6 over 2a. We divided both the numerator and the denominator of this side of equation number 1 by 2, and we got that 6 over 2 equals to 3, and 2a over 2 equals to a. So in conclusion, we found out that according to equation number 1, cosine alpha equals to 3 over cosine alpha equals to 3 over a. We multiplied this equation by a, and then we divided by cosine alpha, and found out that a equals to 3 over cosine alpha according to equation number 1. Then we focus on the right triangle, triangle EDC. So I copy the right triangle EDC, we analyze triangle EDC. This is the right triangle EDC that I copied from the original drawing. In this right triangle, triangle EDC, we know that tangent alpha equals to DE over EC. DE equals to 2, EC equals to A according to our definition. So in conclusion, we found out that according to equation number 2, tangent alpha equals to 2 over A. But according to equation number 1, we have already found out that A equals to 3 over cosine alpha. So we can substitute A in equation number 2 by 3 over cosine alpha. We did it and we got that tangent alpha equals to 2 over A, and A equals to equation number 1 to 3 over cosine alpha. Okay, and here we got that tangent alpha equals to 2 times cosine alpha over 3. We substituted tangent alpha by sinus alpha over cosine alpha. So according to equation number 2, we found out that sinus alpha over cosine alpha equals to 2 times cosine alpha over 3. We cross multiply this equation, equation number 2, and we found out that 3 times sine alpha equals to 2 times cosine square alpha. We have the trigonometric identity that sine square alpha plus cosine square alpha equals to 1. We subtracted sine square alpha from this trigonometric identity, and we found out that according to this trigonometric identity, cosine square alpha equals to 1 minus sine square alpha. So we can substitute cosine square alpha by 1 minus sine square alpha according to this trigonometric identity. We did it, and we got that 3 times sine alpha equals to 2, and here cosine square alpha equals to 1 minus sine square alpha. So we substituted cosine square alpha by 1 minus sine square alpha, and we open the brackets here, and we got that 3 times sine alpha equals to 2 times 1 is 2, and 2 times minus sine square alpha equals to minus 2 times sine square alpha. Then we added 2 times sine square alpha to this equation, equation number 2, and we got that 2 times sine square alpha plus 3 sine alpha equals to 2. We subtracted 2 from this equation, equation number 2, and found out that according to equation number 2, 2 times sine square alpha plus 3 sine alpha minus 2 equals to 0. So here we have a quadratic equation. The coefficient A in this quadratic equation is 2, the coefficient B in this quadratic equation is 3, the coefficient C in this quadratic equation is minus 2. And the variable that we are looking for, x, is sinus alpha. And the general formula for solving the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. The variable that we are looking for here is sinus alpha, so x equals to sinus alpha. So here we will put the data inside this equation, and we find out the value of the values of sinus alpha. Here sinus alpha equals to minus b, b equals to 3, so minus b is minus 3, plus minus b squared, b is 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, a is 2. So it is minus 4 times 2 times c, that is minus 2 over 2a. A is 2, so 2a is 2 times 2, that is 4. So here sinus alpha equals to minus 3 plus minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16, and 16 plus 9 is 25. So inside the root, what is left is only 25. So here we have sinus alpha that is equals to minus 3 plus minus square root of 25 over 4. Square root of 25 is 5, so in conclusion found out that sinus alpha equals to minus 3 plus minus 5 over 4. So here we have two solutions that are possible for sinus alpha. The first solution for sinus alpha is that sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So in conclusion, we found out that according to the first solution, sinus alpha equals to minus 2. But because of the fact that the values, the function sinus can accept ranging from minus 1 to plus 1, and minus 2 exceeds this range of values that sinus alpha can accept. Therefore, this solution is an incorrect solution. In other words, sinus alpha can never be equal to minus 2. So we cancel this solution and we left only with the second solution, that sinus alpha equals to minus 2 plus 5 over 4. Minus 2 plus 5 is 2, and 2 over 4 is 1 half. So we found out that sinus alpha equals to 1 half. And if sinus alpha equals to 1 half, it means that alpha itself must be equal to 30 degrees. And we have this equation that alpha equals to 90 degrees minus theta. So I'll copy this equation here. Alpha equals to minus 90 degrees. Alpha equals to 90 degrees minus theta. And we substituted alpha by 30 degrees because alpha equals to 30 degrees. And we found out that 30 degrees equals to 90 degrees minus theta. Here we added theta to this equation and we subtracted 30 degrees. And we found out that theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees is 60 degrees. So we found out that the angle that we are looking for according to the second method, this angle theta equals to 60 degrees. So in both methods we found out that the size of this angle theta, the angle that we are looking for, it is equal to 60 degrees. Okay, thank you very much.